Hello, everyone. Good afternoon, everyone. Thank you so much for joining us here. I hope you all enjoyed the morning session today, where our senior management outlined the market-based approach that GlobalFoundries is taking and how we're bringing application-specialized solutions in order to serve our customers at the right time. So in this afternoon session, Raj and I will be actually building on that concept. What we will be covering is 5G solutions for smartphones and tablets. Just to give you a little bit of a map of what to expect, I'll be first giving you a high-level market overview of 5G. I'm sort of preaching to the choir when I talk about market overviews here. And then I'll be deep diving into RF front-end module and transceiver solutions. I'll then be handing over the baton to Raj, who will be covering analog power, eNVM, and display driver solutions. The world of 5G is very much upon us. When I say this, we love to talk about the launch of 5G and so forth, but let's look at a couple of proof points. So if you followed the press recently, we've noticed that about 16 major markets worldwide are switching on their commercial 5G networks this year. This is after, in 2018, when US and South Korea actually turned on their 5G networks. The second proof point that we have noticed is mobile operators are estimated to spend about $160 billion in CapEx. That number is right, $160 billion in CapEx in order to upgrade their 5G networks to get ready for the onslaught of 5G. So given this amazing spend rate, let's look at some of the applications at a high level that are going to be initiated because of 5G. So let's take remote control, for example. In both personal and professional lives, the number of objects are actually growing. So all individuals want greater control over their assets. So they want tactile internet applications to come to the palm of your hand, and 5G is going to enable this. Let's take another example. Let's talk about on-demand info. So think about the last time you've actually gone searching for a decent Wi-Fi network in order to have a video chat or to download high-definition videos onto your mobile device. So with 5G, the last mile problem is expected to be resolved, and you can do this over a network. Not only that, health and security are expected to become ultra-reliable, and AR/VR is expected to become a reality. So the most recent article that I read about Ericsson, where Ericsson had actually mentioned that if you are using an AR app for 30 minutes a day in a mobile device, that's going to consume about 40 gigabytes of data per month. That is a staggering amount of data, and 5G is absolutely needed in order to help us address this data deluge that's coming towards us. It doesn't stop there, actually. 5G is going to transform the way we're going to do resource management. It is going to help us build smarter buildings and cities. Entertainment is going to be readily available. On top of that, you're going to have safer and smarter transportation. Think about connected cars, which are going to be talking to each other at extremely high speeds with very low latency, less than 1 millisecond latency. All of this is going to be possible only if you have a high-speed 5G network. So intelligent connectivity through 5G is set forth to drive the next industrial revolution. So Industrial Revolution 4.0 is going to happen because of 5G. So given all of these amazing things that are coming towards us, let's look at it from the perspective of smartphones and tablets and how smartphones and tablets are expected to be a part of this transformation. So the essence of it is always going to be controlling it from the palm of your hand, whether it be an IoT application, being infotainment, virtual assistants, or streaming videos that happen today, or whether be it emerging applications like AR, VR, or connected cars. The idea is to be able to have intelligent connectivity from the palm of your hand. So I'm preaching to the choir here when I say that we're running out of bandwidth, right? We are running out of the number of bands have exponentially grown, and we have completely run out of bandwidth. So in order to address this 5G network, there are 3 new bands that have been released: the 28 gigahertz, 39 gigahertz, and 47 gigahertz. Another proof point for us to look at the importance of these bands are, if you followed FCC recently, the 24 gigahertz band actually went for a $2 billion auction, and that's against 3,000 bids. That shows the importance of these bands. So given the availability of these bands, they're going to enable applications which have extremely low latency, very high bandwidth, high throughput, and high spectral efficiency. A lot of these applications are going to be available because of the availability of these bands. So now let's turn around and look at what it means from a silicon content standpoint, because that's all the area that we play in. So this is a little bit of a map going from 2G all the way to 5G. Going from 2G to 5G, there's going to be a 10x growth in silicon content. What is more interesting and actually way more relevant for us is going from 4G to 5G, the silicon content is going to double. This is a result of the fact that the number of bands are growing. So you're going to have 15 bands. We've had 15 bands roughly in 4G, and that's going to double, get to 30 bands. The number of filters in a 4G phone, 4G device is about 40 filters, and it's going to double essentially, getting close to 75 filters. And all of this is going to drive the silicon content in a saturating mobile market. So it is no secret that the refresh cycles of the mobile market have slowed down. I mean, not everybody is buying a $1,000 phone. So given the slowdown in the refresh cycles, the silicon content still continues to grow. And that is because of the proliferation of bands that is coming our way. So this is actually a very good place for us to be. So given this, let's look at how, from GlobalFoundries' standpoint, we bring in application-specialized solutions in order to address this burgeoning market. Greg, earlier today, in his talk, mentioned about the platforms that we have, the application features, and multiplying that with the amount of IP that we bring to the table, we have tens of thousands of specialized application solutions. So what I'm going to do in my next few slides is going to take you through some of the application solutions for RF front-end module and transceivers. I'm going to be talking about 2 solutions for sub-6 GHz and 2 solutions for millimeter wave, and then handing over the baton to Raj to talk about the rest of the parts of the phone. So in order to set the stage up, I need to talk about the coexistence of 4G and 5G. This is no secret, right? I mean, today, you all know that we actually still have 3G in many parts of the world. It's not like when 5G rolls out, 4G is going to disappear overnight. That's not going to be the case. 4G is still going to be very much in existence in our phones. So hence, the silicon content is expected to very much grow. That is a good place for us to be. So when you look at a very simple block diagram, you have the application processor, the modem, the transceiver, and the front-end module. So if I'm going to draw a high-level map of solutions that GlobalFoundries offers, we have the FinFET technology that addresses the modem and the application processor. We have the FinFET RF technology that actually addresses the transceiver and for 4G. And then we have a hybrid solution where it's RF SOI, GaAs, and SiGe. Of course, we don't do GaAs, but we cannot ignore the fact that the cellular PA market is very much dominated by GaAs solutions. However, the Wi-Fi PA market is very nicely addressed by both silicon germanium and SOI. Now, I'm going to switch gears and talk a little bit about 5G. So in 5G, the modem remains the same with FinFET. From the transceiver standpoint, we not only have a FinFET RF solution, but also an FDX RF solution. And from a millimeter wave front-end module standpoint, we have the capability to address it with both FDX RF and RF SOI. So here's where GlobalFoundries differentiates itself, because depending on your architecture approach, we have a specific solution that fits your needs. That is the beauty of having multiple platforms coming at the architecture from different angles. So now, let me talk about one of the solutions in sub-6 GHz. So 8SW is the flagship technology right now for GlobalFoundries for serving the sub-6 GHz market, specifically around switch and LNA performance. We have industry-leading R-on-C-off parameters that we can talk to you more in detail offline. We have the integration capability of integrating the switch LNA, and we bring it in a very fast time to market in a 300mm platform with best-in-class RF models and technology enablement. So let me talk specifically about the roadmap of 8SW. 8SW was released in production back in end of 2017. And every year, our technology gurus have been driving yearly features onto this platform. So we have released our set of features in 2018, namely the high Pmax switch, the low VT FET. And there are features that are being added this year, namely the low VT FET, the enhanced LNA, and the low harmonic switch. All of these features are essential to serve specific application needs. Given the uptick in demand that we are seeing and the adoption that we are seeing in 8SW, which is incredible in the market, and thanks to a lot of you in this room, we are also transferring this technology over to our Singapore facility called Fab 7. And the qualification of this technology will be complete in March of 2020. The transfer of this technology is going very well. It's going to be a seamless experience for all of our clients. We're not going to stop there in terms of development. We are actually going to introduce a set of features in 2020 that we'll be announcing shortly. So let me pick up a specific proof point on 8SW and demonstrate the value of this technology. This is a proof point of a device called a high Pmax device, a feature that we've added to the 8SW platform. The graph here actually compares, on the left-hand side, you see an axis for millimeter square. This is the core area. On the right-hand side, you see increasing channel lengths of the same device. So when you look at the high Pmax device, that actually provides a 10x gate current improvement. It enables lesser stacking, and it also lowers the area. So when you look at 3 Pmaxs that are compared against for the same device with different channel lengths, you notice that for a 50 dBm Pmax device, the number of stacks actually starts to reduce. The number of stacks reduces from 10 to 6. That offers approximately a 50% area reduction from a core area standpoint. So think about what that translates into multiple switch throw counts for a specific device. So this is an example of a particular feature that we're enabling in a very mature, production-proven platform in order to serve an application-specialized solution. So let me switch gears and talk about the millimeter wave side of the house. Before I talk about millimeter wave, I need to actually set the stage because this is a million-dollar question that I would say has generated a ton of interest in the industry. What I'm going to be specifically talking about is the SOI side of the house. There's obviously a bulk argument associated with it that we can do maybe over a couple of beers or something. The way you want to think about the 5G millimeter wave architecture, this is a very simple view of the world. An antenna subsystem, a FEM subsystem, transceiver, and a baseband application processor. So when you look at this subsystem, we have 2 solutions, and we have essentially differentiated that based on the PA performance that we have seen. So when we look at this particular architecture, there is the 45 RF SOI solution that serves for the PA performance greater than 23 dBm PSAT. And then there is the 22 FDX architecture, which was built on a PA performance of about 20 dBm. So the FinFET continues to address the modem and the application processor. So given these 2 technologies that we have available, and both of them production proven, let's look at the roadmap of each of these technologies. So when we look at the 45 RF SOI platform, the performance has been proven in the market. A lot of our clients have already adopted 45 RF SOI, and the proof is in the pudding because we just announced $1 billion in DVIN today in the 45 RF SOI platform. So that is the proof in the pudding that this technology has gained significant traction in the market. This has the capability to handle greater than 23 dBm PA PSAT with greater than 40% PAE. And you look at the integration capability, it integrates the switch, LNA, and the PA, and has the capability to integrate phase shifters and data converters. It does have extremely fast time to market. It's silicon-proven technology in production today by one of our key partner clients that we have. And we have the capability to enhance the PA FET further. And I'll talk briefly about the PA FET enhancements that we're working on today. Not only that, we're focused on bringing in the REL expert enablement. This is something a lot of our clients have asked for in order to get an early look at the PA reliability. This is not trivial to do, and a lot of you already know that this is something that GF has been focused on for the last 1 year in order to enable REL expert in the market. So let's look at the actual roadmap. If you're looking at the 45 RF SOI roadmap, you have, we introduced the platform by the end of 2017 with a version 1.0 PDK release. We released an early version of the PA FET model because a lot of you were interested in the early enablement on the PA FET model, end of 2018. And we have completed the enablement of the PA FET model 1.0 PDK by earlier this year, May of 2019. We will continue to have innovation happen in our next generation technology. We've not publicly announced it, so hence I'm not mentioning the name of the technology. Please feel free to talk to me offline, and I can go into details about the next generation version of the technology that's going to be brought up in our Malta facility. So A lot of features have been added onto the 45 RF SOI platform. Like I mentioned, the enhanced PA FET, the Cadence Rel Expert, Caliber Fill Gen being one other capability, and it is also being transferred over to Fab 8 in Malta. So the next gen, like I mentioned, is coming in 2020, and I'll be happy to talk to you offline about it. So let me talk about a proof point in 45 RF SOI. So 45 RF SOI delivers best-in-class front-end module performance. It's positioned as a millimeter wave front-end module technology. If you look at some of the recent PA performance data that they have, the PSAT here, as you can see, the PSAT here that you can see has a 20 dBm PSAT with a PAE of about 45.15%. What's actually more interesting on this particular device is the 10-year operation, reliable output power at 17 dBm. This is 17 dBm linear power with a PAE of about 42%. This translates essentially to better thermal efficiency, better battery life, higher performance, as you all know. What's equally impressive is the LNA performance. We've seen noise figures down to 1.3 dB, and this is silicon measurement, has 30% better noise figure, and enables superior signal reach. What's actually not talked about a lot and tends to be ignored by my friends on the bulk side is the switch performance. The switch performance is unequivocally better in SOI as compared to bulk technology. So the insertion loss that we have seen here is 0.65 dB, which has greater than 50% better insertion loss than any bulk technology that we have seen. When we are coming, what's coming next, like I mentioned, is the millimeter wave 5G platform focused on mobile, a new reference design that's targeting an improved PA performances in first half of 2020, and LDMOS reference work that we're doing in order to address the Wi-Fi 6 market. So the 22FDX solution benefits. So let me flip and talk about 22FDX. Needless to say, it's a low-power platform. I think it's very well understood with its operating voltage down to 0.4 volts. It has the integration capability, again, proven because of the leading-edge node capability of 22FDX. Yeah, it is extremely RF optimized. It's an SOI technology. Yes, it's fully depleted, but very good RF performance that we have proven, and I'll show you proof points for. And last but not the least, it has a very good cost profile. It does provide up to 10% dice reduction and up to 50% module cost savings. And these are savings that we've actually estimated by doing a reference design. And I'll be very happy to talk you through the proof points offline about this. So let's talk about the roadmap of this platform. So 22FDX platform, the RF platform, was released in production end of 2017. A lot of you actually would be surprised that the RF version, the initial RF version, which is the sub-6 GHz version, was actually released in production in end of 2017. What we have released this year is the millimeter wave 1.0 PDK. This has been a huge milestone for us because we have spent our time characterizing the millimeter wave capability of this platform. And not only that, we've actually built proof points to prove the front-end module integration capability of 22FDX. And we're not stopping there. Our technology team is working on the next feature enhancement of 22FDX, and this would be coming out in end of 2021. So in 2021, like I mentioned, millimeter wave qualified, Cadence Rel Expert, again, one more feature that we've added for 22FDX, and reference design work to target the Wi-Fi 6 market. The other major announcement that we are going through, the other major tranche of work that we're going through is to align when our 12FDX platform is going to come to market. This is going to be aligned with the timing around client needs at this time. So let me switch gears and talk about some of the proof points. So if you look at the PA performance here, you're looking at a PSAT of about 17 dBm. We also have a PA that's demonstrated up to 20 dBm. So I can talk to you offline about that. And the PAE of about 40.5% with a gain of about 16 dB. If you're looking at the total power savings, it's looking at about 20% total power savings, which results in very high performance and better thermal efficiency. The LNA performance is actually quite similar. If you actually compare the LNA performance between 45 and 22, the LNA performance is actually quite similar between those two technologies, and the switch performance also is quite similar. So both of them have demonstrated equally impressive switch and LNA performances. So given this, there are two different approaches any customer can take when it comes to both of these platforms. You can migrate from, you can do a more integration-centric approach with 22FDX or a more front-end module-centric approach with 45 RFSY. So those are the two approaches that we've normally seen in the market. So last but not the least, I want to talk briefly about the 12LP FinFET RF technology that we have. This technology is built for high-performance, less than 8 gigahertz transceivers. It has demonstrated industry-leading FTF max greater than 330 gigahertz. If you're looking at the power, the ELVT device is a feature that we've added that delivers 20% power savings in the local oscillator as compared to the SLVT device. If you're looking at an area efficiency, it has a 0.064 micron square SRAM device. And from an enablement standpoint, we've also continued to build reference designs for the FinFET RF technology. A lot of you think about FinFET RF, and there is obviously the white elephant in the room with the 16 FinFET technology from our competition. However, where we are differentiating ourselves is the capability to bring in the front-end module expertise that we have on the other side of the house and showcase the integration of Wi-Fi front-end modules. So I'll give you a little proof point for that in a couple of slides. So from what we've announced in 2019 is 12LP 1.0 PDK RF in production release. It was released in August earlier this year. Like I mentioned, greater than 330 gigahertz in Fmax and an EG device for a 3.3 volt PA, and a derivative device, RF device that's coming out in 2021. So let me talk a little bit about a proof point for the Wi-Fi space. So if you look at the PA that's put here, or demonstrated here, it's got a PSAT of about 28 dBm with an average PA power average of about 15 dBm. And this has an efficiency of about in the mid-30s. And when you're looking at the overall technology, it does provide better thermal efficiency for Wi-Fi PAs. Not only that, if you look at the LNA performance on this platform, there are two LNAs that are on offer. One is with a low power LNA with DC power of about 1.6 millivolts with a noise figure of about 2 dB, and a low noise LNA which has a noise figure of about 1.5 dB and a DC power of about 5.6 millivolts. So there are two different options in terms of features that we provide our clients for their design. So what's coming next for the FinFET offering is an optimized 3.3 volt LDMOS for the high-end Wi-Fi market and a few other RF derivatives that we're working on. So in summary, Bami and Greg and Mike and everybody in our SLT always say, think RF, think GF. That is true not only for the front-end module portfolio that we have, but it's for the entire suite of RF platforms that we have at GF. We don't stop there. We also have an RF Wave partner program. A lot of partners are actually in the room here today, and we'd like to thank them for their support. And we continue to offer global shuttles where you can have very fast time to market. So given the breadth of RF platforms that we have, when you think RF, think GF, and with that, I'll pass on the baton to my friend Raj.
So I'll build off of what Shankaran talked about in the modern smartphone. He talked about mainly RF products and technologies. I'll talk about analog power, NVM, and display drivers. Okay, so here you see highlighted some analog power products that go into a smartphone. Wireless chargers, power management or PMIC chips, which have integrated LDOs and DC-DC converters, envelope trackers for better power efficiency, audio amplifiers, and haptic sense ICs. Just to remind you of what we discussed earlier this morning, you or most of you build products, and we deliver solutions. Okay, so an example of a product could be a wireless charging. This is an example of a receiver. You also have a transmitter, but you might build this receiver device. And we have a solution that builds off a platform like 130LP, and then we add features on top of that. For example, a 24-volt LDMOS, an AP-MOM capacitor, maybe some MTP NVM solution, and that a combination is what we call a solution, and in this case, it would be 130 BCD Lite would be a solution that you build your products on. Okay. And through the course of my talk, I'll pick on a few examples of products that we've enabled, things that were really barely existent 6 or 7 years ago, and now seem to run in very high volume. Okay, so the first example is a wireless power system. This now seems to be ubiquitous, right? In 2019, we'll exit at a 1 billion unit rate, okay? And building from there, it's growing at 30% CAGR. So, and it started in smartphones, but really picked up in wearables and hearables, where the form factor is such that it's tough to insert a cord into this and charge. So this has really picked up now. And then it's going up in power too. So where smartphones use about 15 watts, and then wearables, hearables are down to 2 watts, you are seeing companies work on applications that go north of 100 watts. Okay, for example, kitchen appliances and also power tools charging. Okay, we actually also have a customer, so you know about in-vehicle charging, where you have a mat and you drop your phone there. We have a customer that has this similar thing on the basket of a scooter, okay, where you drop this is an e-bike, an e-scooter, you drop your phone on this basket and it charges also. So the trends, you can see now over 1 billion units. The trends in this market, as I mentioned, higher power. Okay, this is for faster charging, but also for different applications that require more power. And then going through glass with higher Z gap. So the current standards are 3 millimeter gap, but moving to 12 millimeters. And the goal here is you have, let's say, a camera outside your house or motion sensor. You want to power that without putting a lot of cable through. And you can charge that from a transmitter that is inside your house. And also having one mat that can charge your watch, your earbuds, your cell phone, etc. on one mat. So having single controllers control multiple devices. And then lastly, if you happen to put your wallet on this mat, you don't want to fry your smart card chips. So you have integration now of NFC type foreign object detection. So all of this is driving higher voltage devices, more efficient devices, integration of NVM, MTP, and also small radios onto these wireless power charging chips. Okay, so that's what's driving it. So now panning out to our different offerings. So that was one example. We have analog power, or what we call BCD Lite and BCD offerings that go from 180 nano all the way actually to 22 nano. So 180 nano was the first one where we actually pioneered this concept of BCD Lite, which doesn't have a full epi stack and barrier stack, etc. It has multiple wells to create isolation. And so it is a much lower cost, very useful for mobility, where voltages don't get very high and where your transients are better defined. So the BCD Lite technology goes up to 30 volts for fully isolated, and then up to 65 volts for what we call ISO body. And then we have a 700 volt solution. This is low side drive solution that goes up to 700 volts. It's triple resurf, about 120 million centimeter squared, specific on resistance, and that is also available on 180 nano. Now, we have a Gen 2 solution that we are currently sampling different customers. There's about 9 products that are in design and have taped out, and we're sampling different customers on Gen 2, and this would have a 30% RDS-on improvement compared to Gen 1. Then moving on to 130 nano, which was our first 300 millimeter BCD Lite solution. This is a very versatile platform. So you have firstly up to 30 volts, the Gen 1. And then we have expanded that up to 85 volts we started out with automotive. So this is a true BCD solution, which has deep trench isolation with poly and a full buried layer, etc. And this goes up to 85 volts. Very popular for automotive applications like battery management, motor drive, motor control, etc. Okay, and then we are further enhancing that with Gen 2, just like 180 nano. where we would have a significant RDS-on improvement. And then because vehicle electrification, you heard Bami and Greg talk about this, is becoming so popular, and there's need to reduce costs, we are offering a 200 volt, this is still in development, it'll start being offered next year, a 200 volt SOI solution also for these kind of applications. We developed 3 years ago a 55 nano BSD light. This was started out with 12 volts for boosted amps, audio amplifiers, haptics, and so on. And now it has been expanded to 30 volts, and then we're working on a 40 volt solution. And we keep adding features to this. I won't have the time to go through all of it, but we're adding MTP and NVM, also looking at chrome side resistors for some of these things, Hall effect devices, air core inductors, eventually moving to magnetic inductors, and so on. So if you need more details, we can talk offline. Then moving down the nodes, we've started work on a 28 nanometer solution. So this work has just started. We'll have a PDK drop in April of next year and select a few customers, early customers to work with on that. And lastly, a 22 nano, we have up to 6.5 volt LDMOS used for Wi-Fi PAs, used for envelope trackers, USB chargers, and applications like that. Okay, so a very broad suite of applications. So we talked about different nodes, voltages, and great RDS-on. That doesn't mean anything unless you have a good analog-friendly PDK. Okay, this is so you can get your designs right the first time. Okay, so not just having corner models that are good, but also modeling mismatch, modeling flicker noise accurately, modeling self-heating for these power devices. And then because these are, as I mentioned, we pioneered BSD Light, you want to look at substrate current injection. And so we model our isolated LDMOS as 6-terminal devices, so you can get information about substrate current injection and also diode reverse recovery as you move from forward to reverse or reverse to forward bias and have a collapse of the space charge region. So these things are accurately modeled, used by sophisticated designers to get their designs first time right. Okay, and along with that, of course, we have our design kits talk about layout best practices and design for manufacturing type solutions. Okay, so we talked about getting your designs first time right. And also, you don't want to over-design. I mean, that's one way to reduce the risk, but that adds cost and also could create some performance issues. So we have rather sophisticated SOA work that we do. I was asked to remove the axis, but the x-axis is VDS, y-axis VGS, and we get breakdown voltages at different temperatures. Those are the curves on the right, and the curves on the left are HCI contour plots for different degradation times, 0.2 years, 1 year, 10 years, and different temperatures. Along with that, we don't provide those limit conditions, we provide aging curves for different voltages and temperatures. So the user can say, oh, okay, GF has this 12 volt device, but the breakdown voltage is really 23 volts, and I'm using it mainly in switching mode. I'm not operating at peak ISUB. And I look at the aging curves and determine that maybe I can use this 12 volt device, so-called, but have it operating or boosted up to 15 or 16 volts. And sophisticated designers do this analysis working with us and our characterization data, and actually can squeeze more performance and have smaller die as a result of it. Now coming to, I guess no analog power presentation is complete without some RDS-on information. So we have steadily improved our RDS-on from our first generation, which was 180, and we did 130 nanometers, and then with 55 nano, we picked up a few tricks on resurf tricks with low-cos and ultra-shallow trench, etc. And then we've taken that back to 180 and 130. So you can see 130 nano here is you can see the Gen 2 here is actually got similar performance to the 55 nano device. And then lastly, we're going to extend that to 28 nano capability also. So to summarize the analog power portion of my talk, we do have best-in-class performance on RDS-on QGD, and we get this from our customers, by the way, and we're always looking for feedback. So if you think, no, you're drinking your own Kool-Aid here, let us know, okay? Because we believe with Gen 2, we are equal to or better than the competition here at the voltages we offer. And we have a rich feature set. We go the gamut of voltage from 5 to 700 volts. We have different kinds of capacitors, dual MIM cap, low TC resistors, echo inductors, etc. And then we put a lot of pride and effort into our enablement. Mike Cadigan talked about this a little bit, and we believe this is our secret sauce to have accurate models, both in RF and analog power. Okay, and then last but not least, proven manufacturing. So this journey started in Singapore on 200 mm, and then we were one of the first foundries to take it to 300 mm, also in Singapore. And now we're enabling Fab 1. So 180, 130 will stay in Singapore, but 55 nano, 40 nano, 28 nano analog power NVM technologies will also be run in Dresden, which we call Fab 1. That's Dresden in Germany. So this gives us a lot more capacity. So we've run over 4 million wafers. We're auto grade 1 qualified, and we have multiple fabs. Okay, and this is important for both high volume mobility customers and auto customers. Okay, so moving on. So I'll talk about NVM next. So this is more specifically embedded NVM. And embedded NVM is used for 3 reasons. One is for secure transactions. Secondly, for over-the-air updates. And thirdly, for storing. And over-the-air updates, you may need to change your calibration curve if the operating system is updated. And then lastly, having customer-specific configuration. So a customer might go into multiple sockets, and they may have different operating systems, and they may want to have an inventory that can be flexible across these different end customers of this. So those are 3 main reasons for having NVM. And you can, I'll just talk about embedded NVM rather than MTP, which is mainly flash, going into camera modules, and also going to GPS. This is for storing local geographical information, SIM cards and NFC, and then also accessory authentication, which is becoming quite big. So to prevent third-party accessories that might damage your smartphone. Okay. Okay. So now my second example is an NFC. This also was barely existent 6 or 7 years ago. It turned out that NFC has been developed in around 2000 timeframe by Sony using the so-called Felica standard, and NXP also was one of the co-inventors in the 2000 timeframe. And the key trick was to prevent, while you're making transactions between 2 people, have a protocol that prevents man-in-the-middle attacks. Okay, so for that you need to have one shared secret and one secret that you don't share, and have some algorithms that allow this communication. And for that, you have to have some amount of data stored that is erasable, writable in flash. Okay, so that was the growth of NFC, enabling secure commerce using your smartphone, but now also being used for other applications, vending machines, train tickets, also peer-to-peer communication across devices. And I talked about wireless chargers. It turns out for hearing aids and things, people are looking at NFC charging all the time into your hearing aid using less than 1 watt power. Okay, and so this market is also continues to grow. It's already quite big, but continues to grow at 6% CAGR. Okay, so now in terms of panning out again into our different embedded NVM solutions, we have on 180 nano, we have an MTP solution. This is writable about 100 times. And this solution actually turns out to be very useful for 8-bit, 16-bit microcontrollers going into white goods, so wildly popular actually in the China market for appliances and so on. And then 130 also has MTP, but it's the first place where we started adding NVM. So we have an E-squared PROM that's a 5-mask adder, and an flash ESF1 with SST that is a 4-mask adder sitting on top of BCD Lite. Then on 55 nanometers, we have a full eFlash, the so-called ESF3 solution, using 13 masks, and we're adding MTP. So this ESF3 is in volume production. Some of the applications are indeed NFC and automotive. So it's ATV1 qualified and is actually ATV0 capable, and we're working on that also. So 55 nano, 130 nano are in volume production. 40 nanometers is now qualified, the process frozen, and we expect it to go into production. There's some designs that are going through their debug process. We expect it to go into production by the end of next year. Okay, so we've just started working on 28 ESF3. Okay, and I'll talk a little bit about it in my next slide. So 28 ESF3 will be our next node. And then 22 is where we have MRAM. And you heard some discussion on that in the morning. So this is a very disruptive technology. Power consumption for write erase is 10x lower than what you might get for flash. Very high speed access times, and could be quite interesting. It's a 4-mask adder technology. So we'll start with IoT and consumer applications, and then we will move to more ruggedized applications, including automotive. Okay, so just in tabular form, all our nodes we have ROM and OTP capabilities. MTP is on 180 and 130, and then flash on 130, 55, 40, and then just started work on 28, where our first PDK drop is actually next month, and we've already chosen a few selected customers to work with, and then these lighthouse customers will continue. We'll have a 0.5 PDK drop in April, and then we'll move on from there. We'll open it up towards the end of next year to more customers. In terms of MRAM, as I mentioned, 22 nano, and this process is actually frozen. It will be considered qualified in Q4 of this year and go into production next year. Okay. So now talking a little bit about 28 ESF3, we're quite excited about this actually. So compared to 40 nanometers, it has 2x the logic density, 40% less power, compared to other alternatives. And we looked at a lot of alternatives, obviously, before we started. Things like RRAM, you have a programming window collapse, and they work well only for consumer grade, while our eNVM, we expect it to be auto grade capable, certainly mobility capable. Compared to other emerging memories, it doesn't have as wide a read margin, and therefore you can't do things like analog compute. You heard this morning about the MAC, the so-called multiply accumulate used in AI, and we do have a lead customer looking at 28 ESF3 for AI type applications. And then lastly, our gate-first technology has significant architecture advantages. So by the way, the trick in all these kind of value-added solutions is to not perturb the base CMOS and not perturb the IP, so that customers can use these things in modular ways and reuse IP across different products. So the ability to integrate BCD Lite and NVM on gate first turns out to be a lot simpler problem. So just by way of a proof point, we can do ESF3 integration with 11 mask adder compared to competitors using RMG that require 17 to 18 masks. That's a huge improvement in cycle time, cost, etc. So we're quite excited about this. So to summarize the eNVM portion, now we believe we have better endurance. So often we spec our technologies to 200,000 cycles. And we spec them quite rigorously, as you might imagine our auto customers require, right? So it's not just you take a few arrays and run it through endurance and retention. We have to do statistics that prove that it is 1 ppm or lower in terms of error rates at at the temperature extremes with 90% confidence on a 16 megabit array. Okay, so quite rigorous testing. We have an innovative roadmap. I talked about MRAM and 28ESF3. We are also looking at an RRAM solution for 12 nanometer. We are not ready to announce that yet, but we're studying it quite deeply. Our bit cells are incrementally actually smaller than the competition. For example, our 40 nano is 0.067 micron squared, and the competitors at 0.07. So 4 or 5% improvement, and that counts for something. And then proven manufacturing. Again, there are, you can write a lot of papers and show data. It's a question of having products out in the field, probably in phones that you're carrying right now, that are doing very critical applications. So more than 15 years of manufacturing ENVM in cars, in phones, etc. We've shipped more than 500,000 wafers that are 300 mm equivalent. And again, we started this in Fab 7 in Singapore, but also now bringing up Dresden, what we call Fab 1. Okay. And then my third example, I'll talk about AMOLED display drivers. So again, this was barely used 6 or 7 years ago. LCD was what was the standard. Now, it turns out AMOLED, they generate their own light. So as a result, in a dark scene or something, you can turn the individual pixels off. So it does have power savings, because the LCD has a white backlight that is always on. You also can get higher contrast because you can literally turn the light off on individual pixels. And you have a wider gamut because you're generating 3 colors of LED light individually. Lastly, you have these trends going towards curved displays, foldable displays, etc., and that is enabled more on AMOLED, and I don't think it's possible on LCD displays. So this is taking market share. The number of smartphones being sold is roughly flat year over year, but this is picking up market share from LCD and growing at about a 10% CAGR rate. Okay. So what you need on an AMOLED for an AMOLED display drive is you need to have, of course, the logic, the 1-volt logic to drive SRAM and so on. But you also need 20 volts because you do have a amorphous silicon TFT backplane that gets driven off 20 volts. And then you have an analog 7-volt system that takes inputs from a DAC, and that controls the brightness of the LED, the individual pixels. So the trend here is towards higher or faster refresh rates, so you can do things like gaming, also to more resolution, going from HD to FHD to QHD. And you can think of this like in terms of TV formats, going from 720 to 1080 and to 2K and then 4K pixel densities. So higher pixel densities, faster refresh rates, that is what is driving more SRAM to store images and buffer the images correctly. And then lastly, as I mentioned, going from rigid displays to more flexible and foldable displays. So this drive towards more SRAM and having this triple gate oxide process, now we're on our 3rd generation of our offerings. So we started at 55 nano. And we always tried to push the SRAM 1 generation further. So at 55 nano, we were the first guys to offer immersion lithography that allowed the SRAM to go to 0.3 micron squared. And then at 40 nano, we actually used a cut mask or double patterning, which is not normally done at 40 nano, by the way. And we had a 210 cell for that. And then at 28 nano, which is our gate first high-K metal gate process, we're at 0.12 micron squared SRAM. And then last but not least, we're going to work on a 22 nano solution. This will allow extremely low power consumption. Okay, so it will allow you to operate at 0.5 volt VDD and should really be useful where you have large format displays like foldable screens and so on. Okay, so 28 nano, 28 HV is now our latest generation. It's in high volume production. So compared to this is our third generation, so we know how to run these parts, we know how to manufacture these parts in volume. It does have the smallest SRAM bit cell. Actually, we're the only guys doing 28 nano in volume production right now. We have a leadership roadmap that takes you down to 22 with our FDSOI solution. And we do believe we have area advantage both in the SRAM and in the analog-friendly MV-HV layout because we don't have CMP limits like the RMG guys do. So this is technology runs in Fab 1 in Dresden. Yields are now at 94% or D naught of 0.04. So quite a mature process. There are about 5 products running on this, and there are several phones already out in the wild with this 28 nano technology. So I'm done with the examples, done with the 3 technology families I want to talk about. I just want to give a shout out to a few other things. Okay, we're a foundry, so we deliver solutions, we deliver wafers. All right, so we started this journey of value added in Singapore with 200 mm and then 300 mm. Now the journey is well on its way in Fab 1 also. So 55 nano BCD Lite, and then going to 28 nano BCD Lite, 28 ESF3 for flash, 28 HV, and then eventually 22 HV for display drivers. That will be done in Fab 1. And I should not forget Shankaran's RF technologies started in Fab 9 in Burlington, but now run in Singapore and run in East Fishkill. So we cover the world with our technologies. We're in stable geographies. We value IP, so we have this thing called the GF Shield technology, GF Shield, where your IP is controlled. We are for secure products going into NFC and SIM cards and so on. We have a certification that's called EAL6 certification. And there are things like if you have a scrap wafer, you don't just grind it and use it as a test wafer. You actually have to destroy it into sand and so on, so it cannot be misused. So we've got this certification, and we have multiple customers doing very secure products in our fabs. Okay, so this is just a list of different customers that have audited us recently. We get audited at least once a month in these fabs. Okay, mobility customers, industrial, multi-market, automotive, especially automotive, not just our customers, but OEMs come and audit us. And we have done very well in these audit results. So you're welcome to come and visit our fabs also. We even have some customers, fabless customers, that get trained in our fabs because they don't have fabs of their own, so they do some orientation training in our facilities. Okay, just want to do one more shout out to our turnkey services. Mike Cadigan talked about a little bit. So for smaller customers, or even actually some big customers, we do offer end-to-end solutions. So not just wafer fab, but we can take control of the packaging, bump assembly, test process, and then drop ship it to either your warehouse or to your customer directly. Okay, and this includes engineering efforts, so engineering, test development, debugging, yield improvement, and also package selection design. So end-to-end, we offer these turnkey services for you. And then one more shout out building off of Cadigan's presentation. So we do foundation IP, we do complex IP, that includes IOs and standard cells, SerDes, and so on. But we also have NVM services, and this includes MTP, Flash, and certainly MRAM, where either we do it ourselves or through our partners. And you can see some of our partners, Synopsys, SST, YMC, etc. And this is also seamless to you. So while we may work with our partner, it's a one-stop shop as far as you're concerned, and we will provide you a macro that has been debugged. So just in conclusion, we talked about 5G phones and how you have critical elements like 45 RFSOI where you can't build 5G phones without it. But then there's all kinds of other technologies and solutions that go around this that enable the phone to be useful. And actually now shown some of these technologies from 180 BC Lite to 55 BC Lite, 40 NVM, 7SW, 8SW. So a wide variety of applications. I can't show you the full universe of devices and products, but we believe we've got you covered on your 5G journey. Okay, with that, I'd like to thank you.